This from the November 2018. Question 11. The threshold frequencies of cesium and potassium metals are given in the table below. 11.1. Define the term work function in words. This is the minimum energy that is required in order to eject electrons from a metal surface. 11.2. Which one of the following metals in the table has a higher work function? Give a reason for the answer by referring to the information in the table. The work function is given as Planck's constant multiplied by the threshold frequency. So whichever metal has the highest threshold frequency will have the highest work function because H is a constant. So here the answer should be potassium. The threshold frequency of potassium is greater than that of cesium. The simplified diagrams below show two circuits, A and B, containing photocells. The photocell in circuit A contains a cesium metal plate, while the photocell in circuit B contains a potassium metal plate. Ultraviolet light with the same intensity and wavelength of 5.5 times 10 to the exponent of -7 meters is incident in the metal plate in each of the photocells, and the ammeter in circuit A registers a current. By means of a calculation, determine whether the ammeter in circuit B will also register a current. So the only way that circuit B will register a current is if the energy that is supplied by the photon is greater than the work function. So if we calculate the energy of the photons and find that it is greater than the work function, then there will be like a registration in the ammeter of circuit B. So on top of there, we are given the threshold frequency. So if we calculate the frequency of the incident light and then we find that it is greater than the threshold frequency of potassium, then there will be a registration in the ammeter. So here we will say the frequency should be equals to C all over lambda. This is 3 times 10 to the exponent of 8. And then the wavelength is 5.5 times 10 to the exponent of -7. So I'm getting 5.45 times 10 to the exponent of 14 hertz. This is the frequency of the ultraviolet light. So 5.45 is less than, so you see the frequency of the light that is provided by the ultraviolet light is less than the threshold frequency. Therefore, no current will be registered because the frequency that is provided by the light is less than the threshold frequency of the potassium. So (11.4). calculate the maximum kinetic energy of an electron that is ejected in circuit A. Energy should be equals to the work function plus EK max. So we are searching for the EK max. This right here is H multiplied by C all over lambda. The work function is Planck's constant multiplied by the threshold frequency, EK max. 6.63 times 10 to the exponent of negative 34 multiplied by 3 times 10 to the exponent of 8 all over the wavelength is given as 5.5 times 10 negative 7. This is 6.63 times 10 negative 34. And the threshold frequency of cesium is 5.07 times 10 to the exponent of 14 plus the EK max. Therefore, the EK max should be equals to 6.63 times 10 negative 34 multiplied by 3 times 10 to the exponent of 8 over 5.5 times 10 to the exponent of negative 7. Subtract by 6.63 times 10 negative 34 times 5.07 times 10 to the exponent of 14. So I am getting 2.55 times 10 negative 20 joules. 11.5. How will the maximum kinetic energy of the ejected electron calculated in question 11.4 change when the intensity of the incident light increases? So a change in the intensity of the light only affects the number of photoelectrons that are ejected per unit of time. The kinetic energy is not affected. The energy that is supplied by the light remains the same. So this will be remains the same.